Let's start with some log stuff because there's one kind of thing we should still probably talk about. And then we'll talk about some sequences and then some limits. Today is 15. But before we do any of that, I should mention, I probably should have mentioned last week, but I forgot to. On Thursday, I will not be here, so we will not have class on Thursday. I will select 1 or 2 videos from the last time I taught 17A for you to watch, probably covering limits and or continuity or some of both. And that'll be the stand-in for class on Thursday. So I'll post an announcement as well on Canvas, but just saying it here and now, we will not meet in this room on Thursday. So don't come. I won't be here. All right. Let's do this. So let's say we have the following. I kind of want to leave that here. Cool. So let's say we had this data. We were given these 3, like you probably weren't even given this one, to be honest. Oh, sorry, let me make it big like this. Let's say we had that data. You don't have to write this down. And we're asked to figure out, is the original data exponential or power function relationship based on having the plot of x versus log, or I should say just the data points of x versus log y and the data points of log x versus log y. So how do we do this without plotting it on the scatter plot and figure out what the best fit line is? So our job here really is to figure out which of these is a linear relationship without like using all the great tools we have. So what we're typically going to do here is we're going to take 2 data points, actually I should say 2 sets of data points from each of the 2 columns. And then what we're going to do is we're going to find the slope between those. So here's what I'm going to do. I'm going to pick in the columns E and F. I'm going to write these down and then I'm going to stop sharing this so you can see them right now. But I'm going to pick, I'm going to round to the nearest, I guess to the nearest second decimal place. So in columns E and F, here's what I'm picking. My first XY data point points are going to be 2, 0.36, and the next one next to it, 2.8, 0.0. I don't love that. I might even go 3 decimal places there. Yeah, 361 and 0.025 is what I'm going to round to. And then I'll pick also say like the last 2 data points. I'm going to have 4.2, negative 0.38 and 5.5, negative 0.64650. Make sure I've written those down correctly. And then from the other 2, same deal. We're going to pick 0.301, 0.360. And the one below it, 0.447, 0.024. I guess we can notice here that the y values are the same, right? They're both log of y. And then we'll pick the last 2, which are also kind of gross. 0.623, negative 0.380, and 0.740, negative 6.50. Sorry, 0.650. Ugh. All right. Oh, sorry. Let me get myself on camera here. Apologies. 1 second. Great. Okay, so then we're going to look at the slope between each of these 2 pairs of points in each of those and figure out if the slopes here are essentially the same or the slopes here are essentially the same. So whichever pairs of points have the same slopes, that is the one that's the linear relationship, which is terrible, which I would probably, so right, we're thinking of this as an XY coordinate, this is an XY coordinate, this is an XY coordinate, this is an XY coordinate. So we're going to find the slope between these 2 and the slope between these 2. And if those 2 slopes are the same, what we're saying here is that essentially we have points like this. These 2 points and these 2 points, and the slope between these two matches the slope between these two. And so we can assume that there's a straight line going through them. Versus if we didn't have the same slopes, we would be thinking, oh, well, the straight line isn't the best fit for that. So that's what we're testing here. But now the math, which is kind of terrible. So this, we're going to do, yeah, so these ones minus those ones. So for this, let's call this one 1, this one 2, this one 3, and this one 4. For 1, the slope is going to be 0.025 minus 0.361 over 2.8 minus 2. I guess I need a calculator. So we're going to get, let's see here, 0.025 minus 0.361 divided by 0.8. Oops, let's actually do that first and then divide it by 0.8. So we're getting about negative 0.42. And then let's look at number 2. 2, the slope is going to be, same idea, that minus that. So negative 0.650 minus negative 0.38 divided by 5.5 minus 4.2. And calculating that, we have negative 0.650 plus 0.38 divided by 5.5 minus 4.2 is 1.3. Equal to negative, approximately, negative 0.21. Does not look like a winner. Those look like they're different enough that they're not close enough that we're just off by a little bit of an approximation. So let's check the other two pairs of points and hope that those are the ones that are actually giving us the linear relationship. So let's see here. I have y's over difference of y's or difference of x's. So I'm going to have this. Let's see. Let me just double. Let me double check and make sure. I'm always like, did I actually write down the right thing? Let's double check here. Let me actually look over here so I can see it better. I've got 0.301 and 0.360. Okay, right. Just making sure. All right, looks fine. So we have. Oh yeah, that's the other one. Yeah. This one minus that one. So 3 is going to be 0.00. Oh, not 0.00. Apologies. 0.024 minus 0.360 divided by 0.447 minus 0.301. Doing the math, 0.024 minus 0.36 divided by 0.447 minus 0.301, giving us about negative 2.3. Thank you. And then for the fourth one, we're going to get negative 0.65 minus negative 0.38 divided by 0.74 minus 0.623. And we hope that it's going to be about the same. We'll find out. Negative 0.65 plus 0.38 divided by approximately 0.74 minus 0.623. Yeah, looking good. So this is telling me that this second column of data is the one that is relatively linear. It's also telling me that the slope was about negative 2.3. So then we wanted to find the relationship. All right, so here's what we've got. Unfortunately, we don't have the y-intercept. So what we're going to have to do is we're going to have to say, okay, well, we have that our log of y minus some y value. Oh, you can't see what I'm writing. Apologies. So we have essentially we're doing y minus y1 equals your slope times x minus x1, except we're using log of y's instead of y's and log of x's instead of x's. So we're saying log of y minus one of your log of y values equal to your slope times your log of x minus one of your log of x1 values. So basically, you're going to pick any point that seems convenient here. None of these seem convenient. Hopefully the data you're given, if you actually have to do a problem like this, is a little bit less ugly than the data I've chosen here. I might just go ahead and pick the first one here. So I'm going to say, great, I have log of y minus 0.36 is equal to my slope, which is negative 2.3 times log of x minus 0.301. Let's just say 0.3. So now we've got our equation. I guess I should say, if the question was just to determine the type of relationship, we should know that since the log data was the linear data, that means that the relationship is exponential or power. Power. But we'll see it right here as well. So then if they asked us to actually calculate it, we would do this. So then we'd say, I would isolate the log of y. So log of y is equal to negative 2.3 log of x. And then negative 2.3 times negative 0.3 is positive 0.69 plus 0.36. So we've got that log of y is equal to negative 2.3 log of x plus this number, which is about 1.05. And then we would raise both sides to the powers of 10. So 10 to the log of y equal to 10 to the negative 2.3 times log of x plus 1.05. And then you can solve for y. Y is going to be equal to, rewrite this part as 10 to the log of x to the negative 2.3, and then times 10 to the 1.05. And then simplifying, we get y equal to, I'm going to write this part first, 10 to the 1.05 times 10 to the log of x to the negative 2.3 is x to the negative 2.3. And now we can actually see that it is a power function relationship because you have y equal to x to a power. I would like to hope no one asks you to do it this way because it seems really terrible, but it is totally doable. So if you're given data points that are representative of x and log y and log x and log y, to figure out which one is giving you the linear relationship, you literally just have to find and see which one actually has a slope that's consistent the whole way through. Okay. Any questions about any of that? Yes.
Graphs, but I think you also have like tables. So this would be like the method for.
Sure. Right. But I say if you have the graph already and you can see that the graph is like a straight line, you can, and you're given like the equation of the graph, then I guess it depends on what you're being given. It's hard to know without seeing it. But yes, this is how you would do this kind of thing if you're actually having to kind of come up with the equation of the line based on the data points given, knowing that one of them has to be linear. Right? You can't really do this unless you're starting off with the assumption that one of these tables of data is representing a linear relationship. Otherwise, it just doesn't work. All right, let's continue on here. Let's talk about some sequence stuff. Lots to say about sequences. We talked a bit about recursive sequences last time. I want to say a little bit more about recursive sequences. Yeah, there was one I had in mind. Oh, on paper I wrote down. So let's see. I believe it was something like this. A sub n plus 1 is equal to, it was 10. What was it, James? Sorry, one second. I had one that was really good. Oh, I know what it was. Yeah, minus 1/4 a sub n. That seems right. Yeah. And my a sub 1 is equal to 8. And I want to figure out if this, oh, question, yes. Yes, sorry, it got brought back to me here. Pass it around. So a sub n plus 1, or I'd like to say the next term is equal to 10 minus 1/4 times the current term. So we want to do two things here. We want to write out some terms to kind of see what's happening, and then we want to try to find if the limit exists. So my first term is 8. My second term is 10 minus 1/4 times 8, which is 10 minus 2. Oh, did I stupidly pick the fixed point? So this is a lovely example here. A sub 2 is 8, which means A sub 3 is 8. If this happens, you should think to yourself, well, great, I'm done. The limit exists and it's 8. If you start at 8 and keep getting 8 back, there's nothing else to do. So how unexciting here. It didn't mean for that to happen, but I kind of was getting ahead of myself here. So let's say we have, let's change it up just a little bit. Let's say we have a sub n plus 1 equal to, sure, 5 minus 1/4 times n. And now we're going to start at, sorry, a sub n. And now we're going to start at n equal to 8. Sorry for my very unexciting example there. Sorry, we're starting at, oh my gosh, James. A sub brain. A sub 1 is n. So now if we find some further values in the sequence, we have 5 minus 1/4 times 8, which is 5 minus 2, which is 3. Okay. And then if we find the next one, a sub 3 is going to be 5 minus 1/4 times 3, which is 5 minus 3/4. Most of the time I prefer fractions. Here I start using decimals because I feel like it's just easier to write down. That's going to be 4.25. A sub 4 is going to be 5 minus 1/4 times 4.25. And things just start getting messy. That's going to be 5 minus 1.0625, which is something gross like 3.9375. So it kind of looks like we might be bouncing around, I don't know, 4. We started above 4, we went below 4, we're above 4, we're below 4, and we're pretty close to 4 there. So I'm guessing that 4 is probably what we're getting closer to. But what I probably should have done first is just found the fixed points. So find the fixed points, also called the equilibria. We're going to set each a sub n plus 1 and a sub n equal to usually L. So we have 5 minus 1/4 L equal to L. Or I should say L equal to 5 minus 1/4 L. A little.
Okay.
We got a lot to say. There's like, you guys asked to see like this and continuity and a lot. So I'm trying to make sure we see the things you guys are asking for. So here, I'm going to add 1/4. Actually, I'm not going to add 1/4 L. I'm going to make a better choice. What am I going to do first? What can I do to make solving this a little easier? What can I multiply by? 4. Get rid of that fraction. Then we have 4L equal to 20 minus L. If I add L to both sides, 5L is equal to 20. Divide both sides by 5. 20 divided by 5 is 4. So there's our only candidate for the fixed point. And it seems like our terms are getting closer and closer to that. So it's reasonable to say here that we think the limit as n goes to infinity of our sequence is equal to 4. Bless you. Some other sequences. People asked about a couple that looked like this. So let's say we had something like a sub n equal to 4 to the n plus 3 over 5 to the n. We're curious about what that sequence is doing. Well, this kind of falls into a category of something raised to the nth power. In fact, we're going to come back to this one in just a second. So first, we should look at the following. If you have something like this, a sub n equal to 1/2 to the n power. Let's write out some terms and see what happens. So we're going to get 1/2 to the first, 1/2 squared, 1/2 cubed. And every time to get to the next term, we're just multiplying by 1/2. 1/8 times 1/2 is 1/16. 1/16 times 1/2 is 1/32. And it seems like as we go on and on and on, the terms are getting closer and closer to 0. And that's typically true if you're multiplying by a number that is less than 1. If every time you multiply by a number that's less than 1, the resulting thing is smaller than it was before. That's actually more generally true if our value is between -1 and 1. So if you have something like a sub n equal to negative 2/3 to the nth power. You start writing out terms. The first term would be negative 2/3. And then negative 2/3 squared is positive 4/9. And then multiply by another negative 2/3, you get negative 8/27. Positive 16/81. And as we go on and on here, the denominator is going to outpace the numerator. And that fraction is going to get closer and closer to 0. So both of these sequences have limits that are 0. And I would say very generally, if you have a number, we usually call it R, it stands for the word ratio. If your ratio is between -1 and 1, then we can say that the limit as n goes to infinity of that ratio raised to the nth power is going to be 0. Because it's exactly this kind of deal, where you keep multiplying by a number that's making it get closer and closer to 0, whether or not it's bouncing back and forth between positive and negative or not. On the other hand, if your ratio is bigger than or equal to 1, this isn't going to be the case. If our sequence was something like b sub n equal to 3 to the n, and we start writing out terms, the first term is 3 to the first, the next term is 3 squared, the next term is 3 cubed, the next term is 3 to the fourth. Clearly, our terms are getting larger and larger and larger, and it's not going to stop. We keep multiplying by 3, things just get bigger and bigger and bigger every time. So this sequence diverges. Diverges, you could say, to infinity. Or writing as a limit, the limit as n goes to infinity of 3 to the n is infinity. And that's true, well, that idea holds whether you have a positive thing larger than 1 raised to the power, or a negative thing more negative than -1. So if you had something like b sub n equal to -4 to the nth power, then your terms would bounce back and forth between positive and negative, but they would still get further and further away from 0. -4, positive 16, -64, positive 100, or sorry, 256, -1024, etc., etc., etc. Here, we would also say that our sequence diverges. You couldn't say to where, though, because every other term you're getting positive, negative, positive, negative. So here this just diverges, and the limit doesn't exist. If you asked about the limit as n goes to infinity of -4 to the n, we would say it does not exist. Yes, technically it's true that this limit also does not exist, but we're just being more informational about how it doesn't exist. So back to the question that generated this whole conversation. What about this sequence here? 4 to the n plus 3 over 5 to the n. Well, if I write out a few terms, I can start to see what's happening. So writing out the first term, I'm going to get 4 to the fourth over 5 to the 1. And I don't really want to simplify that, because what I want to do is look at the next term. If n, and that's where n equals 1. If n equals 2, I'm going to get 4 to the 2 plus 3, which is 4 to the fifth, over 5 squared. If n equals 3, I'm going to get 4 to the 3 plus 3, over 5 to the third. What, if we don't even think about it, it seems like the pattern should be that the next one should be 4 to the what? And over 5 to the what? Right, every time the power for both the numerator and the denominator is increasing by 1. So it looks like every term we're multiplying by what? Well, we multiplied on top by 4, on the bottom by 5. So every term we're multiplying by 4/5, a number that's less than 1. So we're multiplying by 4/5, by 4/5, by 4/5. So what I would say is my ratio here is 4/5. That means this sequence is going to converge to 0. Because if you multiply by a number that's smaller than 1 enough times, it's going to get smaller and smaller and smaller and smaller and smaller. Now, that might not feel very satisfying, and I've kind of run out of room here, so let me move down here. A more kind of analytical way of doing that, sorry, I know it's kind of terrible to covering things up in all the wrong ways here, apologies. So what I'd say here is another way to deal with this is to say, for a n equal to 4 to the n plus 3 over 5 to the n, we're going to rewrite this as 4 to the n times 4 to the third divided by 5 to the n. And then we can rewrite that as 4 over 5 to the n times 4 to the third. And then, sorry, if we're going to take the limit of that, the limit as n goes to infinity of 4 over 5 to the nth power times 4 to the third. Well, this expression here is exactly the thing we just said. Our ratio is between -1 and 1. It's being raised to an ever-increasing power, so it's going to get closer and closer and closer to 0. So we're going to get something that is equal to 0 times 4 to the third, which is still 0. So this sequence converges, and it converges to 0. There was one other sequence that was really on my mind, but yeah. Right. Let me give you one more like this, just because there's something kind of sneaky here. Oh, I know what it was. Yeah. What if I had something like 8 to the negative n plus 3 to the negative n? And I want to know if this converges or diverges. And typically when we ask this, the question is all, does it converge or diverge? If it converges, what does it converge to? That should always be part of the question. Well, not very nicely written like that. I would much rather rewrite it as 1 over 8 to the n plus 1 over 3 to the n. Which you could either leave as is, or you could even rewrite it as 1/8 to the nth power plus 1/3 to the nth power. But either way you express this, we can see that each of these pieces have either this way, the denominator is getting really large, so the whole fraction is going to get really, really close to 0. Or this way, we have this kind of deal where you have some number that's between 0 and 1 getting raised to a higher power, so it's going to get closer and closer to 0. So either way we write this, we can say, oh yeah, the limit as n goes to infinity of 1 over 8 to the n plus 1 over 3 to the n is equal to the limit as n goes to infinity of 1/8 to the n plus 1/3 to the n. But either way, that's going to be 0 plus 0, which is 0. So this sequence converges to 0.
Would you have to like write all that down or like on the test or which?
Good question. How much do you need to write down? For which one? For this one or that one? The second one. So I think you could, I think if I was doing this on a test, here's the work I would show. I would say the limit as n goes to infinity of 8 to the negative n plus 5 to the negative n. I would always encourage rewriting powers so that it seems like you have a power that's positive infinity. Right now, the way this is written, it looks like I have 8 to the negative infinity because n is getting infinitely large, and 5 to the negative infinity. And to me, that just doesn't work as well. So I would rewrite it one step. Say I have the limit as n goes to infinity of 1 over 8 to the n plus 1 over 5 to the n. And then it's easy for me to believe that I know that 8 to the n is going to be really, really big. So 1 over 8 to the n is going to be really close to 0. So then I would say that this is equal to 0 plus 0, which is 0. That is the work I would show on an exam for this problem. Okay. Yeah, we should do that. So, you've got this example here. Not you. So all this is kind of in this word I'm looking for, I can't find. We're using this so we can do something with a geometric series. So let's talk about a geometric series. So far we've been talking about sequences, which is just a list of numbers. A series is when you take that list and you add up all the terms. So for example, here's a geometric series. 1 plus 1/3 plus 1/9 plus 1/27 plus 1 over 3 to the next power plus 1 over 3 to the next power. And it just goes on and on and on. The hallmark of being geometric is that each subsequent term is the same multiple of the previous term. So I like to think of it as, oh, 1 times 1/3 is equal to 1/3. And 1/3 times 1/3 is equal to 1/9. And 1/9 times 1/3 is equal to 1/27, and so on and so on and so on. So here I would say my ratio is equal to 1/3. That's what I'm multiplying by every time to get to the next term. Another equally good way to determine what your ratio is, or to see this geometric, is to take any term and divide it by the previous term. If I take, say, for example, 1/27 divided by 1/9, that's the same as 1/27 times 9/1, which is 9/27, which is 1/3. I could have made the easier choice and picked 1/3 divided by 1. But for any choice here, if it's a geometric series, you should be able to take that number, divide it by the previous number, and it should always equal the same ratio. So then we're going to write this in a slightly more convenient, well, convenient maybe is not the right word, a slightly more useful way. I'm going to write, this one as 1 plus 1 times 1/3 plus 1 times 1/3 squared plus 1 times 1/3 cubed plus 1 times 1/3 to the 4th, and so on and so on. And you might even view this first term as 1 times 1/3 to the 0th power. So you can think of, we're really just adding up a bunch of things where we're increasing the power by 1 every time. And let's do one more example. Let's say we had something like this. Let's say we had another geometric series, 8. I'm sorry, it's not a sequence, it's a series, James, no commas. 8 minus 4 plus 2 minus 1 plus a half minus a fourth, et cetera, et cetera, et cetera. I want all of you to take a moment and find the ratio on your own paper or tablet or whatever you're using, or you're inside your brain if you want. So one way you could have found the ratio is by taking -4 and dividing it by the previous term, +8, and reducing that to get -1/2. Or pick any term and divide it by the previous. The easiest choice would have been to pick either -1 and divide it by 2, or 1/2 and divide it by -1. But any choice should yield the same result if it is geometric. Side note, if you do that and you don't get the same result for two different choices, it means it's not a geometric series. That shouldn't be the case in this class, but there are other classes where you talk about series, and like one thing you do is try to see if it's geometric first before you actually talk about it being geometric. So here's how I'm going to write this one. I'm going to write this as 8 times -1/2 to the 0th power plus 8 times -1/2 to the 1st plus 8 times -1/2 squared plus 8 times -1/2 cubed, and so on and so on and so on. The reason we're doing this is because it's going to allow us to find a formula for what the first so many terms add up to. So here's what I mean. So let's say we have a very general first n terms of a geometric sequence. Series. So I'm saying first n terms, it's actually the first n plus 1 terms because of how things work out here. So we're going to say that Sn, this is called the nth partial sum, is equal to your first term, and then your first term times your ratio, and then your first term times your ratio squared, and so on forever and ever and ever. Actually, not forever and ever, ever. Sorry, it's the nth partial sum. We're only going out to the nth term. Now I'll point out, this is actually n plus 1 terms. You don't need to worry about it too much, but I just don't want to be like, hey, James, you have n plus 1, not n. That's the way it's usually done. Even though it's called the nth partial sum, you're usually adding up n plus 1 terms because this is the 0th term. And then here where the power is 1 is the first term, the power is 2 is the second term, and so on and so on and so on. Okay, now we're going to do some tricky algebra. Tricky, yeah, it's a little tricky. So here's what we're going to do. We're going to take this expression and we're going to multiply each side of this equation by r. So we're going to say we have r times Sn on the left side, and we're going to multiply each of these by r. So we're going to have a times r plus a times r times r plus a times r squared times r plus a times r cubed times r plus all the way to a times r to the n plus 1. And aside from a couple terms, almost every term shows up in both this one and that one. In fact, I'm going to underline them. All these terms and all these terms, and there's one like right there before, right? There's a times r to the n right there. So the only ones that don't show up in both of these are the first term here and the last term there. Everything else shows up once in each equation. And now what we're going to do is we're going to subtract these equations from each other. So we're going to do this equation minus that equation. So on the left side, we're going to have the nth partial sum minus r times the nth partial sum. On the right side, we're going to have all of this, a plus a times r plus all the way to a times r to the n minus all of this, a times r plus a times r squared plus all the way to, I'm going to write the last two terms, a times r to the n plus a times r to the n plus 1. And what's going to happen is on the right side, almost everything's going to cancel out. The a times r minus a times r is 0. The a times r squared that would be there is going to cancel out the minus a times r squared that would be there. All the way to the very last term, the a times r to the n here is going to cancel out the minus a times r to the n there. So what we're left with is, on the left side, Sn minus r times Sn. On the right side, a minus a times r to the n plus 1. And so then what we can do to solve for Sn is factor out an Sn on the left. So you have Sn times 1 minus r. Factor out an a on the right. You have 1 minus r to the n plus 1. And then divide both sides by 1 minus r to get that the nth partial sum is equal to 1 minus r to the n plus 1 divided by 1 minus r. Oh, don't forget the a on top. Apologies. It's kind of a lot. Back to the example we were doing. Let's say I want to actually find out what the first 4 terms add up to. So let's say for, you're always in the way. Sorry. So let's say for that first one, we want to know what S4 is equal to, which would have been 1 plus 1/3 plus 1/9 plus 1/27 plus 1/81. And you know what? I'm going to do it 2 ways just so you can see that the formula really does work. So just adding these up, I'm going to do the common denominator, which is kind of terrible. Well, let's do it real quick. So I'm going to get 81 over 81 plus 27 over 81 plus 9 over 81 plus 3 over 81 plus 1 over 81. Oh my goodness, it's awful. And then you have 81 plus 27 is 108, plus 9 is 117, plus 3 is 120, plus 1 is 121. So you get 121 over 81. Okay, that wasn't the worst thing I've ever done. But let's use the formula and see that the formula actually works. So using this formula here, I'm going to say that S4 should equal my A value, which is 1, right? My A is the first term. In fact, let's write that down. A equals 1 and R equals 1/3. So it should be A times 1 minus 1/3 to the n plus 1. So my n is 4. So I should be raising that to the 4 plus 1 power. Divided by 1 minus my r. Looks kind of gross. Let's find out what it is. So the 1 I don't need there. I've got 1 minus 1/3 to the 5th is 1 over 243 over 1 minus 1/3. Simplifying, 1 minus 1 243rd is 242 243rds. 1 minus 1/3 is 2/3. Flip and multiply. You get 242 over 243 times 3 over 2. 242 divided by 2 is 121. And 3 over 243 reduces to 81. And look, they're the same. So what's the point? The point is that this formula gives you a way of adding up any number of things in a geometric series. So you get out of the first 1,000 terms and just say, here's the formula. So what we're going to do with that is we're going to answer a question. We're going to ask a question, and we're going to answer a question. Where'd you go, question? Sorry. Got all my notes all over the place. Yeah, not you. You. Sorry, it's hard to keep track. There we go. Here we go. Okay. And then this is definitely a question that somebody asked me to do one similar to. So it's a wordy question. It's one of these, you're given a drug every so often, and then the amount reduces, and then you're given the drug again, and you're asked to find various things about this. So here's the setup. And this is, I believe it's problem number 35 from section 2.1, in case you want to go look at it later. Here's the setup. The doctor prescribes a 100 milligram antibiotic tablet. To be taken every 8 hours. Just before each pill is taken, %20 of the drug, antibiotic, from the previous dose remains. Right, so you took the drug, and then after 8 hours, it's down to only 20% of its original amount, and then you take another one. So first question, how much of the drug is in the body right after, just after the second dose, the third dose, the fourth dose? We'll stop there. Not really stop there, but like stop it at that. So typically for a question like this, I would make a table. I find that to be the easiest way to handle this. So I'm going to start on the left with the number of doses. And on the right, the quantity of drug, QN. Wow. I'm sorry about the penmanship. I know it feels like it's worse than usual today. Apologies. I'll try to clean that up a little bit. So after the first dose, how much drug is in the body? I mean, okay, assuming that it's absorbed like rapidly. How much drug? How much? 100 milligrams? 100 milligrams. Okay, then we wait 8 hours. We take the second pill. And from our previous pill, there's 20% of that left. So it's going to be, how do I want to write this? I want to write this that way. 20% times 100 plus another 100 milligram dose. Which we will simplify just to be able to answer the question. That's 20 plus 100, which is 120 milligrams. But actually writing out the next part in a longer way, which I'll show you, is going to be more effective in seeing the formula. So for the third dose, it's going to be 20% of what we had. But I would encourage you, instead of writing 120, write 20% of this amount here. So it's 20% of 0.20 times 100 plus 100, and then we're adding on another 100. Before we simplify this, let's actually multiply it out. So I have 20% times 20%. So I'm going to distribute the 20% here, or the 0.20, whichever way you want to think of that, as 0.20 times 0.20 times 100 plus 0.20 times 100 plus 100. Or, as might be more useful, 100 times 0.20 squared plus 100 times 0.20 to the first plus 100 times 0.20 to the 0th. Oh, it's kind of looking geometric. If you actually want to calculate the value, 0.2 times 0.2 is 0.04. 0.04 times 100 is 4. So we would get 4 plus 20 plus 100, which is 124. Let's take one more iteration just to see if this pattern holds. So if I go to the fourth dose, it's going to be 20% of all that. So let's be smart about this. I don't want to write all the things. So if I take 20% of all of this, I'm just going to multiply each of these terms by another 0.20. So I'm taking all of this and multiplying it by 20%. So I'm going to get 100 times 0.20 cubed plus 100 times 0.20 squared plus 100 times 0.20 to the first. And I'll just say here, this is my 0.20 times the previous quantity. And then I'm adding on another 100. And it looks like exactly like we thought it should look. It's 100 times 0.2 cubed plus 100 times 0.2 squared plus 100 times 0.2 to the first plus 100 times 0.2 to the 0 if we want. This is very much a geometric series, which is why we spent the last 15, 20 minutes talking about geometric series, so we'd answer a question like this. If you actually want the amount here, we could do the math. So 20% of 124. 20%, by the way, I think is an easy calculation if you think about it. You just multiply by 2 and then move the decimal over. So 20% of 124 is, let's see, it's 248, but then move it over. So it's 24.8. That's going to equal 24.8 plus 100, which is 124.8 grams. All right. So that's usually not the hard part of this question. The hard part is the next two parts. So part B, we want to write a difference equation. I do not love that title, but that's what they call it. Or a recursive equation for Q sub n plus 1 in terms of Q sub n. Well, we kind of already did that. In fact, if you look here, you can see right here, I said that Q sub 4, right, because that's what this amount is equal to. This is my Q4, is equal to 0.2 times Q3 plus 100. So if I take that, Q4 is equal to 0.2 times Q3 plus 100. I can think of, well, that's holding every time, right? But like here, my Q3 quantity is exactly 0.2 times Q2 plus 100. And I can, instead of using 2 and 3 or 3 and 4 or 5 and 6, I could use n and n plus 1. So this is making me think, oh, I'm going to get Q sub n plus 1 is equal to 0.2 times Q sub n plus 100. That's usually not the terrible part of a question like this. Usually it's the next part where they ask you to find the explicit formula. This is my opinion, that's the next part. So let's do that. Part C, explicit formula. For Q sub n as a function of n. Well, fortunately, the work we already did up here is already kind of leading us to something, right? We know that Q sub 2 is 0.2 to the first times 100 plus 0.2 to the 0 times 100. And Q3 is 100 times 0.2 squared plus 100 times 0.2 to the first plus 100 times 0.2 to the 0th. And Q4 is 100 times 0.2 cubed plus 100 times 0.2 squared plus 100 times 0.2 to the first plus 100 times 0.2 to the 0. So it looks like we're essentially getting that our Q sub n, in fact, what I should do is factor out the 100 here. The power that we start with, or the highest power we start with, is always one less than the subscript we're on. So I'm thinking we've got 0.2 to the n minus 1 plus 0.2 to the n minus 2, all the way down to 0.2 to the third plus 0.2 squared plus 0.2 to the first plus 0.2 to the 0th. And that's a geometric series. This geometric series here, we know all the things. If you write it out in the more standard way, which I will just to make it clear what's going on, this is 100 times, times, well, I'm going to switch the order of these. So it's 100 plus 100 times 0.2 to the first, plus 100 times 0.2 squared, plus all the way to 100 times 0.2 to the n minus 1. Our A is just 100, and our ratio is 0.2. So our formula is going to be that the sum is equal to, again, A times 1 minus R to the n plus 1 over 1 minus R. You have to be a little extra careful here. Our A value is 100. Our ratio is 0.2. And really the way you should read this n plus 1 here is just, you're going to the power that's 1 more than the power you ended with. The power I ended with here is n minus 1. 1 more than n minus 1 is just n. So that should be a 0.2 to the nth power there, which I know is a little wonky, but that's the way it works out. And on the bottom, we have 1 minus 0.2. I would simplify this. 1 minus 0.2 is 0.8. So I have 100 divided by 0.8 times 1 minus 0.2 to the n. And 100 divided by 0.8 is the same as 1,000 divided by 8, which is 125. This is equal to 125 times 1 minus 0.2 to the nth power. And then if you look at this, you can see what the limit's going to be. Because we have a number here raised to the nth power, and that number is smaller than 1. So we can say, oh, the limit as n goes to infinity of Qn is equal to 125 times 1 minus 0.2 to the nth power. But that 0.2 to the nth power, oh, sorry, I forgot the limit in front of that. That's terrible there. But as n goes to infinity, 0.2 to the nth power goes to 0. So we're just left with 125. So if you kept doing this process forever and ever and ever, you get closer and closer to having a amount of 125 milligrams of this antibiotic in your body. You shouldn't be taking antibiotics forever and ever and ever, but if you did, this is what would happen. I will just say that if you had taken this difference equation, also known as a recursive equation, and found the fixed point would have been 125. I would encourage you all to do that on your own. So you find the fixed point by solving L equal to 0.2 times L plus 100, you should get that limiting value. It's kind of neat. All right. There's an earring up here or something. I don't know if it's an earring or some little pearly looking thing. Sequences. There's lots to be said about sequences. We can't say it all. Let's continue on. Talk more about limits. Last time we talked about limits a bit, right? Right? Yes, no, maybe so. I think so. Sorry, it's hard to remember all the things they talk about. So limits. Did we talk about 0 over 0 types of limits last time? Let me ask a different question. Did we do a limit like this kind of last time? The limit as x approaches 2 of x squared minus 4 over 3x minus 6. Where if you plug in 2, what do you get? You get 4 minus 4 over 6 minus 6. You get 0 over 0, which is could be anything. I want you to take that to heart. 0 over 0 isn't 0 necessarily, or 1, or 5, or 17, or infinity. It could be any of those things, depending on what your expression is. So when you have a limit that's a 0 over 0 type, what I usually like to say, and I might have said this last time, is that when you have a 0 over 0 type of limit, you have to do more work. You have to do some sort of algebra or some sort of other way of exploring what value this expression is getting closer and closer to. Let's look at this one specifically. So for 0 over 0 types of limits, there are typically a few things I do. The first thing I think about is do some algebra, which I know is not very specific. There are a few types of things. One of the things we do is factor and cancel. So for example, here, limit as x approaches 2 of x squared minus 4 over 3x minus 6, we can factor the numerator as x minus 2 times x plus 2, and the denominator as 3 times x minus 2. And since x doesn't equal 2 here, right? Again, I'm going to go back to the, excuse me, the whole idea of a limit as we're asking what this function is getting closer and closer to as x gets really, really, really close, but not equal to 2. Well, as long as x isn't equal to 2, like say x could be 2.1 or 2.01 or 2.00001 or 1.99999, that x minus 2 divided by that x minus 2 will be a number divided by the same number, which is going to be 1. I should say a non-zero number divided by the same non-zero number, which will be equal to 1. So it's totally legitimate to say that x minus 2 divided by x minus 2 is equal to 1. And then we can say, well, really, we're talking about the limit now as x approaches 2 of x plus 2 over 3. Or I would, not usually, but I'm just going to rewrite this as the limit as x approaches 2 of 1/3 times x plus 2. And so now what we're doing is we're asking the question, what does the function 1/3 x plus 2 get close to as x gets really, really close to 2? Well, if x is really close to 2, then x plus 2 is close to 2 plus 2, which is 4. And x plus 2 divided by 3 is really close to 2 plus 2 divided by 3, which is 4/3. Or to make a long story much shorter, plug in 2 for x. And that's a pretty typical way of dealing with a 0 over 0 type of limit, is you essentially eliminate the part that's making it 0 over 0 by factoring and canceling or doing something else we'll talk about. And then after you've gotten rid of that piece that's causing us problems, we can then just toss the value of x in, the x is approaching into the limit and get the nice answer that we were looking for. Let's look at some more examples. In fact, why don't you all try this next one? Try finding the limit as x approaches -3 of x squared plus 5x plus 6, x squared minus 5x plus 6. Yeah, that should be a minus sign, sorry. Divided by x squared minus 9. Try finding the limit of that expression by first doing some factoring and canceling. I'm terrible here. Sorry, that my brain is. It should have been the first one. Let's just make that a limit as x approaches +3. That'll fix it. Sorry about that. Yeah. So if we plug in 3, which we should do whenever we're trying to find a limit, is plug in when x is approaching before we start just whacking away at it. what happens? Well, if I plug in 3, the limit as x approaches 3 of x squared minus 5x plus 6 over x squared minus 9 is equal to 9 minus 15 plus 6 over 9 minus 9, which is 0 over 0. Okay. The reason I say this is because you don't want to just start factoring or trying to mess with it if it's not 0 over 0. If it's not 0 over 0, you might just have the answer. So make sure it is a 0 over 0 before you start just trying to apply the methods here. But it is. So here's something that's nice to know. If you know that plugging in 3 got you 0, then you know that x minus that number should be a factor. So we can see that this should factor as, on top we should have x minus 3 times x with something. On the bottom we should have x minus 3 times x with something. On the top it should be x minus 3 times x minus 2, because negative 3 times negative 2 is positive 6, and negative 3 plus negative 2 is negative 5. On the bottom it should be x minus 3 times x plus 3. And then we can cancel the x minus 3's, or divide them and get 1. And now you're left with the limit as x approaches 3 of x minus 2 over x plus 3. And then you plug in and you get 3 minus 2 over 3 plus 3, which is 1 over 6. But if someone asks you, say, this limit, sorry. Someone asks us the limit says x approaches 3 of x squared minus 5x minus 6 over x squared plus 9. It's very tempting to be like, well, something probably happens to just start factoring it. No, don't start factoring it. Plug in 3 and see what happens. If you plug in 3, you're going to get 3 squared minus 15 minus 6 over 9 plus 9, which is 9 minus 15 is negative 6. Negative 6 minus 6 is negative 12. You get negative 12 over 18, which reduces to negative 2/3. And you're done. So if you can plug in what x is approaching and get a not undefined indeterminate thing, good to go. Let's look at some other algebraic things that pop up here. You might face something like the limit as x approaches 4 of the square root of 2x plus 1 minus 3 over, sure, 2x minus 8. And you don't have to actually write it down, but if we just do a mental check and plug in 4 for x, we can see that in the numerator, we're going to get the square root of 9 minus 3, which is 0. And in the denominator, we're going to get 8 minus 8, which is 0. So this definitely is a 0 over 0 type. But we can't just factor this. I mean, we could factor out a 2 from the bottom, but I don't see, if I do that, that's going to be an x minus 4 on the bottom. I don't just have an x minus 4 on top. There's some other work I have to do before I can factor and cancel. And the other work here is to multiply the top and bottom by the conjugate of the radical part. So I'm going to multiply the top and bottom by the square root of 2x plus 1 plus 3. Over the same thing. Whenever you multiply by a conjugate, the reason we multiply by a conjugate is to get rid of the radical so that we can actually simplify the numerator and pull out the x minus 4 factor that's causing us problems. And whenever we do this, we always actually want to multiply out the conjugates, and we don't want to multiply out the not conjugates. So here's what I would do. In the denominator, I would write the denominator as the following. I would factor out the 2 from the 2x minus 8 and write it as 2 times x minus 4. And then I would just write it as times the square root of 2x plus 1 plus 3. I don't want to multiply this out because I know I'm looking for that x minus 4 to cancel. It does me no good to multiply it out when I know I'm trying to make that term go away. So if you know you're trying to make something cancel out, don't FOIL it out. Don't multiply it out. In the numerator, I'm going to have, so here's the work I want you to show. I'm going to skip this step for a second. Here's the answer that you all should just say from there to there, we get the first thing squared minus the second thing squared, all divided by the nice denominator that I wrote there. That is what multiplying by the conjugate gives you every time. The reason that's happening is because when you multiply this out, here's what happens. You get root 2x plus 1 times root 2x plus 1, which is the square root of 2x plus 1 squared. You get the square root of 2x plus 1 times 3. So that's 3 times the square root of 2x plus 1. You get minus 3 times the square root of 2x plus 1, which is minus 3 times the square root of 2x plus 1. And you get minus 3 times 3, which is minus 3 squared. And every time you do this, the middle terms add up to 0. Because 3 square root of 2x plus 1 minus 3 square root of 2x plus 1 is 0. But you shouldn't do that work. Nobody wants you to do that work. Nobody wants to see that work. Everybody knows that you know that if you multiply these together, you're going to get the first thing squared minus second thing squared. You can show that work if you really want to, but no one is requiring to see that work. So then we're going to get 2x plus 1 minus 9 over 2 times x minus 4 times the square root of 2x plus 1 plus 3. I just lost a point by writing that because I forgot to write the limit. Limit as x approaches 4. And so then the top is 2x minus 8. So I have the limit as x approaches 4 of 2 times x minus 4. I know I said 2x minus 8, but I'm writing it that way. I didn't plan on them exactly canceling, so that's why I already factored. And then we can cancel. 2 divided by 2 is 1. X minus 4 divided by x minus 4 is 1. And we end up with the limit as x approaches 4 of 1 over the square root of 2x plus 1 plus 3. And now finally, I don't write the limit because I'm actually not going to have any x values. I'm going to plug in x equal to 4 and get 1 over the square root of 9 plus 3, which is 1/6. So another algebraic method, if you see a 0 over 0, I'm going to go back a couple pages here, is to multiply by the conjugate. Specifically, if you see a square root plus or minus something else, or something else plus or minus the square root. There's one more algebraic method that I feel like is pretty commonplace. Let's look at the following example. Let's say we have the limit as x approaches 6 of 2 over x minus 1/3 over x minus 6. And we'll double check just to be sure, but if we plug in 6 for x, we get 2/6 minus 1/3, which is 0, because 2/6 is 1/3, over 6 minus 6, which is also 0, so it's definitely a 0 over 0 type. So we do some algebra. And in this case, the algebra that we're going to do is we're going to get a common denominator. And there's actually 2 kind of different ways of doing this. We're going to get a common denominator. I'll show you both ways. So the way that's kind of a little bit more straightforward, but is a little bit more computationally weird, is just to actually get a common denominator. So I'm going to take my limit as x approaches 6, and to subtract these fractions, I need to have a common denominator. I'm going to multiply the 2 over x by 3 over 3, and the 1/3 by x over x. And then the bottom is still just x minus 6. Then we're going to simplify. We get the limit as x approaches 6. This is going to be 6 over 3x. This is going to be x over 3x. So we're going to get 6 minus x over 3x all over x minus 6. For some reason, simplifying fractions and fractions is always kind of challenging. So if I have 6 minus x divided by 3x, all divided by x minus 6, that's the same as limit as x approaches 6, 6 minus x over 3x multiplied by what? Well, dividing by something is the same as multiplying by its reciprocal. Dividing by 2 is the same as multiplying by 1/2. Dividing by x minus 6 is the same as multiplying by 1 over x minus 6. If it helps, and I think it does help, you can rewrite or think of the x minus 6 as being x minus 6 divided by 1. So then when you're multiplying by that, or when you're simplifying this, dividing by a fraction is the same as multiplying by its reciprocal, 1 over x minus 6. And then we're unhappy because things don't quite perfectly cancel. We've got the limit as x approaches 6 of 6 minus x over 3x times x minus 6. 6 minus x over x minus 6. Let me ask you all a question. What's 2 minus 7? What's 7 minus 2? What's negative 5 divided by 5? Negative 1. And that would be true no matter what numbers you picked, as long as they weren't the same as each other. So, right, same deal. If I did 7 minus 1,000 over 1,000 minus 7, those two numbers are always exactly opposites of each other. And when you divide numbers that are opposites of each other by each other, you get negative 1. So whatever you pick for x, as long as it's not 6, then 6 minus x over x minus 6 is going to equal negative 1. All right, pick 3. Don't pick 3. Pick 2. 6 minus 2 is 4. 2 minus 6 is negative 4. 4 divided by negative 4 is 1. And since that's true for any x where x is not 6, this part's equal to negative 1. If you don't like that, I totally understand. You could also just factor out a negative 1 from either the numerator or the denominator. So another way of doing this is saying this is equal to the limit as x approaches 6. Factor out the negative 1 from the top, and you're left with negative 1 times x minus 6 over 3x times x minus 6. And then those just cancel to 1. Either way you slice it, you get the limit as x approaches 6 of negative 1 over 3x, which is equal to negative 1 over 18. I'm plugging in the 6 for x. There is another way to do this kind of problem that feels a little bit slicker, but it's can be, I feel like, just a tiny bit harder to see how or to remember that that's the way you're supposed to do it. So the other way that's just like a little bit more computationally easy, where you don't have to deal with this fraction over a fraction, is you're still going to use the common denominator, but then what you're going to do with that common denominator is you're just going to start off immediately by taking your limit as x approaches 6 of 2 over x minus 1/3 over x minus 6, and multiplying the entirety of the numerator and the denominator by that common denominator, 3x. And if we do that, in the numerator, we're going to distribute that. So we're going to get the limit as x approaches 6 of 2 over x times 3x. The x's will cancel. Minus 1/3 times 3x. The 3's will cancel. Over x minus 6 times 3x. Don't multiply that out because we know that we want the x minus 6 to cancel. So if you already have the thing as you want it to cancel, don't mess with it. So then we're going to get the limit as x approaches 6 of 2 times 3 is 6. 1 times x is x over x minus 6 times 3x. And just like before, 6 minus x divided by x minus 6 is going to give us a negative 1. That's going to be the limit as x approaches 6 of negative 1 over 3x, which is negative 1 over 3 times 6, which is negative 1 over 18. To me, this just feels a tiny bit more computationally easy. I don't have to deal with the fraction and the fraction and the flipping and the multiplying, but really either way is fine. I would do this either way. All right, 325. What do I want to say here? So, oh yeah. So those are the 3 types of 0 over 0 limits where we use algebra. So back to limits for a second. So limits of the 0 over 0 type. The first thing you do is some algebra. So you either factor and cancel, or you multiply by a conjugate if you see a square root, or if you're trying to add or subtract fractions in the numerator or the denominator, you get a common denominator. But then there are some 0 over 0 types of limits that this doesn't work for at all. And I don't remember if we talked about them in this class or the other class on Thursday. Wait, today is Tuesday? Of Thursday of last week. So you'll have to tell me, did we talk about the limit as x approaches 0 of sine x over x? We did? I don't remember if I did or I didn't. So you might have talked about it in your own class. This limit, unfortunately, is kind of challenging in that the proof for this limit is it's kind of an interesting geometric proof, which we're not going to do. So what I would say is, I would say if you want to see it, I'm happy to show you to you in office hours or something. But here is the proof, the evidence that I would like you to take to heart. So let's use some Desmos here real quick. Yeah, we got 3 minutes, plenty of time. Or not, Desmos, come on. So one thing I want to point out, let me look real quick back at the limit. You guys have something? I think I had like a question. No, okay. So I just want to point out, if we look back at one of those limits we did before, like I really want the easy one to graph. Sorry, the first one. So if I graph, wow, oh my, what? Oh, sorry, I'm looking at the wrong thing. So if I look at that first one we did, say y equal to x squared minus 4 divided by 3x minus 6. And you focus on what's happening close to 2. Come on. Yep. So right here, close to 2, we're getting closer and closer to values that are like 1.3, 1.33. But right at 2, it's undefined. But the y values on the other side are very, very close to 4/3, or 1.33333, which we showed, right? We definitely showed that, right? That limit as x approaches 2 of x squared minus 4 over 3x minus 6 was equal to 4/3, even though the graph isn't defined at that one particular point. The reason I point this out is because I want you to look now at the graph of y equal to sine of x divided by x. Let's zoom back out and let's turn this off. So if we look here, it certainly looks like as we get closer and closer to 0 that the y values are getting closer and closer to what number? Everybody. Well, they're getting really close to 1, and we are very, very close to 1. But then when we get to the 0 there, it is in fact undefined. You saw it, right? It's undefined. So if you plug in 0, it's undefined. But I'll remind you all, the limit doesn't care what's happening at the point you're approaching. So it doesn't matter that it's undefined at 0. What matters is that as you get really, really, really close to 0 from either side, the y values get really, really close to 1. In fact, we could also see this if we were smart for a second, if I was smart for a second, and pulled up a table. And just started plugging in some values like 0.9, not 0.9, like 0.1. Really undefined? Let's try that again. Or 0.01 or 0.001. And if you get close enough to 0, it's not actually equal to 1, it's just the approximation is so close to 1 that that's the thing they write on the thing. But right, this is, you get closer and closer to 0, the y values do get closer and closer to 1. So I will end by saying that this limit is equal to 0. And more generally, if you have the limit of sine of some stuff divided by the exact same stuff has to be the same. If it's different, you have to fix it. As long as that stuff is going to 0, then that limit's going to be 1. So for example, I could say the limit as x approaches 2 of sine of x squared minus 4 over x squared minus 4. Do I have sine of some stuff or the exact same stuff? I do. Is the stuff getting closer and closer to 0? Yes, it is, because as x goes to 2, x squared minus 4 gets closer and closer to 0. So this definitely is a sine of 0 over 0, where the zeros are the same. This limit has to be 1. All right, I'll stop there. Thursday, I won't be here. Don't come here. I'm going to make an announcement with a couple of videos that I want y'all to watch, probably covering some more limit stuff and some continuity. I just know office hours right after class today, not on Thursday though, because I won't be here. So on Thursday, there also won't be office hours right after class like there usually would be.